Okay, hello and welcome back. In this video, we're going to cover section 12.5 on the binomial theorem. So this will be a way of expanding out some binomial, which is an expression with two terms. So I can imagine like x plus y. If we raise this to powers, well, if we raise it to the first power, we get just x plus y. If we raise it to the second power, that would give us x squared plus 2x plus 2xy plus y squared. And we can say continue this until we get to x plus y to the nth power. So what will this be equal to? We'll be working on building basically a formula so that we can produce any power of a binomial. To do this, we'll need first the expression n choose k, which you can also write as n choose k. So we'll explain what that is. In order to evaluate this, we also need the factorial expression, n factorial, which means we would take whatever that number n is and multiply by 1 less than it, so n minus 1, then 1 less than that, n minus 2, all the way until we get to like 3, 2, 1. For example, 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So let's keep this in mind, and then we'll first explore this choose operation, and then we'll be able to build our equation for any power of a binomial. So let's first start with this choose operation. And they use j instead of k. So I'll start using j just to go with their notation. So they say that, and I'll recopy it down here, n choose j is equal to n factorial over j factorial times n minus j factorial. So let's look at a few examples and practice evaluating this. So we'll start with part A, 3 choose 1. And I'll write out the formula here. N factorial over j factorial times n minus j factorial. So this should be equal to 3 factorial over 1 factorial times 3 minus 1 factorial. So that will be 2 factorial. I'll write it out first, 3 minus 1. So that would be 3 factorial over 1 factorial times 2 factorial. So you probably have a function to compute this. It probably looks like n with a c and k, maybe, on your calculator, maybe hidden in the statistics operations. But if we need to do this by hand, try expanding out these factorial expressions and see what will cancel. That would be 3 times 2 times 1 over 1 times 2 times 1. So the 2 and the 1's cancel, and we'll just be left with 3. So let's try part 2, or part B. We have 4 choose 2. So this should be 4 factorial over 2 factorial times 4 minus 2 factorial. So 4 factorial over 2 factorial times 2 factorial. So that would be 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1. So 2's and 1's will cancel, and 2 goes into 4 2 times. So it looks like we're just left with 2 times 3 over 1. So positive 6. Part C, we have 8 choose 7. So this will be 8 factorial over 7 factorial times 8 minus 7 factorial. So that's 8 factorial over 7 factorial times 1 factorial, or 8 times 7 times 6 times 5, 4, 3, 2, 1, over, notice 7 factorial will just be from 7 onward here. 7 times 6 times 5 times 4 times 3 times 2 times 1. So all of this would cancel with 7 factorial, and we're left with just 1. So 8 over 1 is equal to 8. So a lot of the terms end up canceling whenever we do this. If you expand out the factorials, you can see what will cancel. So there's a few useful common themes here for this choose operation that we can use. N choose 0 will be equal to 1. N choose 1 will be equal to n. We saw that up here with 3 choose 1, we got 3. N choose n minus 1, so 1 less than it, is also equal to n. We saw that here. 8 choose 7 gave us 8. And then n choose n is equal to 1. So let's see how this will fit into the binomial theorem. And let's define what that is. So this is about expanding some binomial. And they use a and b. I'm sorry, they use x and a here. So let's imagine x plus a to some power n. Our formula to expand this out involves a summation. We'll get a sum of a bunch of terms. And the coefficients of each term will be these choose expressions. So let's write out the summation first, and then see how it will expand. So I'll write it out here. We have x plus a to the power of n is going to equal the sum of, and they use j here, so I'll use it as well, j going from 0 to n of n choose j times a to the power j times x to the power n minus j. So if we expand this out, the first one would be, j is like our counter that will start at 0 and go up to n. So n choose 0 times a to the 0 power, so that will just be equal to 1. And we'll get x to the power n minus 0. So x to the n, that's our first term here. Then our j will just increase until we get to n. So our next term would be n choose 1 times a to the first power times x to the n minus 1 power. And this will continue until we get to n. So it takes a little bit to get used to the pattern, but let's go through some examples to use the binomial theorem. So let's start with example 2. We're going to do x plus 2 to the 5th power. So using our formula, this should be the sum j going from 0 to 5 of 5 choose j times 2 to the j power times x to the power of 5 minus j. So let's expand out these terms, and I'll make a little bit more room here. Let's start on this side. So let's start when j equals 0. This will give us 5 choose 0 times 2 to the 0 power times x to the 5 minus 0 power. Our next term will be 5 choose 1 times 2 to the first power times x to the 5 minus 1 power, so to the 4th power. So notice our powers will just descend on the x's, and the powers on the 2 will increase. So next term will be 5 choose 2 times 2 to the 2nd power times x to the 3rd power. Then 5 choose 3 times 2 to the third power times x to the second power. I'll continue here. So plus 5 choose 4 times 2 to the fourth power. Oops, I wrote x. Times x to the first power. Then plus 5 choose 5 times 2 to the fifth power times x to the 0 power. So let's use a couple of those previous statements to evaluate some of these coefficients. We said that n choose 0 is equal to 1. N choose 1 is equal to n. N choose n minus 1 also equal to n. And n choose n is equal to 1. So that will take care of a few of these, and we'll do the rest of them, we can do the rest of them by hand. So our first term, we have 5 choose 0, so based off of that first statement, that should just be equal to 1. 2 to the 0 power is 1, so we'll just have x to the fifth. Then for our second term, 5 choose 1, that should just be equal to 5 times 2 to the first power times x to the fourth power. Then we'll need to calculate 5 choose 2, so I'll go ahead and write that as 5 factorial over 2 factorial times 5 minus 2 factorial, so that will be 3 factorial, times 2 squared, so this will get multiplied by 4, and we'll have x cubed. Our next term, 5 choose 3, that will be 5 factorial over 3 factorial times 5 minus 3 factorial, so that will be 2 factorial, times 2 cubed, which is 8, times x squared. Then next two terms, we have plus 5 choose 4, that should be equal to just 5, times 2 to the fourth, which is 16, times x. Then 5 choose 5 should be equal to 1, times 2 to the fifth, which is equal to 32, times x to the 0 power, which is also equal to 1. So here we just need to evaluate these two factorial statements, which are actually the same. We have 5 factorial over 2 factorial times 3 factorial. We just have the order flipped in the denominator in the second time we see that. So what is this equal to? Well, this is 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. So the 3 2 1s will cancel. 2 goes into 4 2 times. Looks like this will just be equal to 10. So let's simplify everything, and we'll have our expansion. So our first term will just be x to the fifth. Second term, 5 times 2 is 10, x to the fourth. The third term, that choose term, the 5 factorial over 2 factorial times 3 factorial, we said that was equal to 10, so that'll be 10 times 4, or 40 x cubed. Then we should have another 10 here, this time times 8. So we'll get plus 80 x squared. Then our next term, 5 times 16, also happens to be 80 times 80x. And then last term, 1 times 32 times 1 is 32. So many terms. This is what we would get if we multiplied x plus 2 times itself 5 times. So imagine multiplying another x plus 2, then another x plus 2, and another x plus 2. Oops. So the binomial theorem is very powerful in that it allows us to produce any power of some binomial without having to manually go in and multiply it that many times. Let's still a little bit tricky and takes a little bit of work. However, it produces a lot of really useful results. So let's look at another example to get more practice. Look at example 3. This time we want to do 2y minus 3 to the 4th power. So using our binomial theorem summation notation, this would be j going from 0 to 4 of negative 3 to the j power times 2y to the 4 minus j power. So let's expand this out. Oops, and I forgot our choose. Here, let me scoot this over. So we should also have 4 choose j in front. So let's start expanding this out. First term would be 4 choose 0. Then we'll have negative 3 to the 0 power. And then 2y. This time, this whole thing will be to these various powers, so to the 4th power. So we'll end up with some powers of 2 that will enter into the mix here. Second term should be 4 choose 1 times negative 3 to the 1st power times 2y to the 3rd power. Then we'll have 4 choose 2 times negative 3 to the 2nd power times 2y to the 1st power. Then 4 choose 3 times negative 3 to the 3rd power times 2y. Let's see, did I skip a power? 4, 3. Oh, let's see, this should have been to the 2nd power here, because we'll have descending powers. Starts off at 4 minus 0, 4 minus 1, 4 minus 2. So then our last term would be 4 minus 3, the 1st power. And then our last term, I'll add it in here, would be 4 choose 4 times negative 3 to the 4th power times 2y to the 0 power. So let's start to work through this. 4 choose 0 should just be 1. Negative 3 to the 0 power is 1. So we have 2y to the 4th power. So it'll be 2 to the 4th times y to the 4th. 2 to the 4th is 16. We'll have 16 times y to the 4th power. Next term, 4 choose 1 should be equal to 4. And we have negative 3 to the 1st power. And then 2y cubed. So 2 cubed is 8. And then y cubed is y cubed. Then we have 4 choose 2. We actually did that one earlier in our one of our previous examples, and we got that that was equal to 6. So I'll replace that with a 6. And then we'll have negative 3 squared, so that will give us a positive 9. And then 2y squared should be 4y squared. Then we will have 4 choose 3 should be equal to 4 times negative 3 cubed. So negative 3 squared is positive 9 times another negative 3 should give us negative 27. Then times 2y to the 1st power. Then our last term is 4 choose 4, which is equal to 1, times negative 3 to the 4th power, which is equal to positive 81, times 2y to the 0 power, positive 1. So if we multiply everything out, we should get 16y to the 4th. 4 times negative 3 times positive 8 should give us negative 96 y cubed. Then 6 times 9 times 4 should give us 216 y squared. Then 4 times negative 27 times 2 gives us negative 216 y squared. Then 1 times 81 times 1 leaves us with 81. So this would be 2y minus 3 to the fourth power, 16y to the fourth minus 96y to the third, plus 216y squared minus 216y. Oops, let's see. Should have been y to the first power here. Yeah, y to the first power plus 81. So it takes a bit of practice to get used to the pattern. It's useful to have the general formula and just check to see what you should plug in. And so that's finding every term, but we might be asked just to find a specific term or the coefficient to a specific term. Let's look at example 4. This asks us for the coefficient of y to the 8 in the expansion of 2y plus 3 to the 10th power. So we want to find the coefficient of y to the 8. Well, if we were to write this out, this would be the sum of j going from 0 to 10 of 3 to the j power times 2y to the 10 minus j power. So we need to find what would be our value of j to get y to the 8th power. So notice we would need to subtract 2 to get an 8th power. So that means j should be equal to 2. So let's find just that term. We just want that one term when j equals 2. That would give us 3 squared. Oops, yeah, looks like I forgot the choose piece again, because we need 10 choose j here. Gotta remember to keep that in there. So we would have 10 choose 2 times 3 to the second power times 2y to the 10 minus 2 power. So 10 choose 2, that'll be 10 factorial over 2 factorial times 10 minus 2 factorial, so times 8 factorial, times 3 squared, which is 9. And then this will be times 2 to the 8th power times y to the 8th power. So this just wanted the coefficient, so we need to find out what all of this is equal to. So let's see. 10 factorial over 2 factorial times 8 factorial. Well, this will be 10 times 9 times 8. That will continue over 2 times 1, and then times 8 times 7 times 6. Notice from 8 on top, we'll cancel with the 8 factorial on the bottom. And then we can say 2 goes into 10 5 times. So really it's 5 times 9, which is 45. So let's replace that with 45. We'll have 45 times 9 times 2 to the 8. Let's see, 2 to the 8 will give us 256. So 45 times 9 times 256 gives us a pretty large number. We get 103,680 y to the 8. And it just wanted the coefficient, so we would just be looking for that 103,680. So that's if we're asked for a coefficient, and we could be asked just to find a particular term. So we want the sixth term in example 5 of x plus 2 to the ninth power. So in terms of our summation notation, this would be the sum of j going from 0 to 9 of 9 choose j, won't forget that this time, times 2 to the j power times x to the 9 minus j power. And we just want the sixth term. So notice that we start counting at 0, so the sixth term will actually happen when j equals 5. So I just got to be a little bit careful there. It's tempting just to plug in 6, but we start the count at 0. So let's say when j equals 5, that would give us 9 choose 5 times 2 to the 5th power times x to the 9 minus 5 power. So that would be x to the 4th. So 9 choose 5, that'll be 9 factorial over 5 factorial times 9 minus 5 is 4, so 4 factorial. 2 to the 5th is 32. And then we have x to the 4th. So that'll be 9 times 8 times 7 times 6. Once we reach 5, that's essentially 5 factorial. 5 times 4 times 3 times 2 times 1. So that'll cancel with the 5 factorial on the bottom. And we'll still have times 4, 3, 2, 1. And you can try and cancel as much as possible. The 4 goes into 8 2 times, 3 goes into 9 3 times, 2 goes into 6 3 times. So we have 3 times 2 times 3 times 7, all over 1. And this is still multiplied by 32x to the 4th. So if you multiply that out, 3 times 2 times 7 times 3, we'll get 4032 x to the 4th. This would be the fifth term, or I'm sorry, the sixth term, if we were to expand out x plus 2 to the ninth power. So a pretty powerful method. If you end up taking a class in probability and statistics, you'll work with something called the binomial distribution and calculate binomial probabilities. And so that will rely on the binomial theorem in order to make those calculations easier. We can also see this show up in other fields as well. But here we'll just focus on the mathematical patterns. All right, that will be it for this video. So oops, wrong section. So we evaluated the n choose j statement and practiced using the binomial theorem. So there's a couple different questions you'll see, either just expanding out a binomial or finding a particular coefficient or a particular term. All right, that will be it for this video, and I'll see you next time.